generator. My efficiency, my elution efficiency is 88%. What is my actual yield? 250 millicuries times 0.88. And we know it's going to be smaller because you're not going to get more activity out than what you think is in there. You're going to get less activity out than what you think is in there. So if you divide it and you get a higher answer, you know you did it wrong. You know your answer is going to go down. 250 times 0.88 is 220 millicuries. Actual yield. All right. Now, if the theoretical yield is 850 millicuries and your actual yield is 727, what's the efficiency? Well, we're going to take what we actually got, 727, divided by how much we think is in there, times that by 100. 86% efficiency. All right, one more. We're going to throw it all together. The generator was last eluted 20 hours ago and had 3,500 millicuries at that time. If you elute it now, how much technetium will you get? The generator has an elution efficiency of 89%, and the 20-hour Tech-Mol ratio is 0.83. So the first thing I have to do always is figure out how much moly do I have. 20 hours ago, I had 3,500. So A sub T equals 3,500. E is the negative 0.693 divided by 67. If you use 66, that's fine. Times 20. Your answer will be close enough to get the multiple choice. Punch in your calculator, 3,500. I have 2,846 millicuries of moly. Step 2, how much technetium do I have in there? What's my theoretical yield of technetium? I have to multiply by the 0.83. $2,362 millicuries of technetium. That's my theoretical yield. Now my actual yield is the theoretical yield times my efficiency. My final answer is 2,102 millicuries technetium actual yield. All right, moving on. Radionuclide purity. Radionuclide purity is microcuries of moly per millicurie of TAC. We don't change the units. So if we have 800 millicuries of TAC and 80 microcuries of moly, 80 microcuries of moly over 800 millicuries of TAC, my ratio, 80 divided by 800 is 0.1. My unit is microcuries of moly per millicurie of TAC. If it's less than 0.15, it passes, at least as of right now. But what I know is this ratio is going to continue to go up. All right, we can ask this a different way. How many microcuries of moly are allowed in a TEC eluate that contains 1,200 millicuries? Always think conversions. 0.15 microcuries of moly equals 1 millicurie of TAC. So if I have 1,200 millicuries of TAC, whatever's on top goes on bottom, millicurie of TAC, microcuries of moly on top, 0.15 microcuries of moly per millicurie of TAC. Millicurie of TAC cancels. 1,200 times 0.15. Gives me 180 microcuries of moly that I can have if I have 1,200 millicuries of TAC. All right. You have 22 microcuries of moly and 800 millicuries of TAC in your TEC eluate. What is going to be my radionuclide purity in 4 hours? Now I have to do 2 different decay problems. I cannot get around that. You have to do it twice. So I'm going to decay 22 microcuries of moly, e to the negative 0.693 divided by 67 times 4. 2. I have 21.1 microcuries of moly. And then I have to do the same thing to technetium. I have 800 millicuries. But I've got a shortcut with technetium, right? 800 millicuries divided by, not divided by civil. I'm going to times that by 0.891 to the fourth. 800 times 0.891 up caret 4. Now I have 504 millicuries of tech. So I just do my ratio, 21.1 microcuries of moly over 504 millicuries of tech, 21.1 divided by 504, in 4 hours, my ratio is 0.04, and again my unit, microcuries of moly per millicurie of tech. Alright, now, when does my generator eluate expire? So it expires in 12 hours, unless it expires before then. 12 hours is max. So a generator eluate has 70 microcuries of moly and 1,400 millicuries of technetium. And we want to know how long before the ratio gets to 0.15 microcuries of moly per millicurie of tech. There is an equation to do, and I'm going to show you it. If you forget it, I'll show you how you do it is how we just did the last one. But I am going to show you the equation. The equation is T equals negative Ln. We're going to put our ratio here, divided by 0.1052 minus 18.03. Okay, so that's the equation. It's a lot of numbers to remember. Now, what goes in that parentheses? The parentheses is 70 microcuries of moly over 1,400 millicuries of tech. So we put that in our calculator, 70 divided by 1,400, and we have 0.05. So that's what goes in the parentheses, 0.05. Now, we put that in our calculator, hit negative Ln. Do not hit second Ln, just hit negative Ln, and on your screen it should look like negative Ln with an open parentheses. 0.05, close your parentheses, and hit enter. It should say 2.995. Divided by 0.1052, hit enter. It should say 28.47. Minus 18.03, enter. My answer is 10.4 hours. So it expires in 10.4 hours because that's before 12 hours. If it was more than 12 hours, it would still expire at 12 hours. Let's do another one. Tech eluate has 85 microcuries of moly and 450 millicuries of tech. When will it expire? We're going to take our 85 microcuries over 450 millicuries. 85 divided by 450. We've got a ratio of 0.19. It's already expired. So if you get a problem like this, check and make sure it's not already expired. It's expired as soon as it reaches 0.15. If I were to throw this in my calculation, negative Ln, 0.19 over 0.1052 minus 18.03, my answer would be a negative number because it already expired. All right, radiochemical purity. What are we doing with radiochemical purity? We want to know how much hydrolyzed reduced we have or how much free tech we have. I always recommend finding the percent impurity because if you do a two-strip test, you have to find the percent impurity. So you might as well always find the percent impurity. So we're going to do a one-strip test. And in our one-strip test, we want to know the radiochemical purity of Tech MAA. The top of the strip, we'll draw a picture, the top of the strip has 1200 CPM, and the bottom of the strip has 22,500 CPM. Now the rule is that free tech goes to the top, because it's free to fly away. So that means that this top is free tech, and the bottom is Tech MAA. I'm going to find the percent radio chemical impurity. I want to find the percent of free tech. So I'm going to take my free tech divided by, here's where the mistakes are always made, you have to divide it by the total. Times that by 100. 1200 divided by 1200 plus 22,500 times 100. It's 5%. What does that tell me? 5% free tech, 5% radiochemical impurity. Always look at the question. Is it asking for radiochemical purity or impurity? It's asking for the purity. What I have just found is the impurity. To find the purity, 100 minus 5 is 95% purity. All right, now we're going to look at hydrolyzed reduced tech. So you're checking your tech eluate for hydrolyzed reduced tech. The bottom of the strip, which is the hydrolyzed reduced tech, has 22 microcuries. The top of the strip, which is your technetium, your eluate, has 1.4 millicuries. I have to convert this. So 1.4 millicuries, 1 millicurie is 1,000 microcuries. So 1.4 times 1,000 equals 1,400 microcuries. So I'm going to put my 1,400 microcuries up here, and that's my technetium. Not free tech, it's my tech eluate. So the hydrolyzed reduced is something that happens to the tech eluate. So you can do the hydrolyzed reduced first, before you even put it in a kit. So I want to find my percent, it says radiochemical impurity. So I'm going to take my 22 hydrolyzed reduced, divided by 22 plus 1,400, times that by 100. 22 divided by 22 plus 1,400, times it by 100. 1.5% hydrolyzed reduced. Has to be less than 5%, by the way. All right, last one here, two-strip test. If you get this on your board exam, if it's the NMTCB, that means you're probably doing really good. Because the NMTCB, what happens, if you get a question right, they reward you with a harder question. So if you're sitting there and these questions are like incredibly hard, you're like, I've never seen these before in my life, that probably means you're doing well, so don't give up. All right, two-strip test, we're gonna draw pictures. So on the first strip, hydrolyzed reduced, it has 1,000 counts at the bottom and 21,300 at the top. My hydrolyzed reduced is at the bottom. This hydrolyzed reduced is heavy, so it stays at the bottom. On the second strip, my free tech, it has 42,500 at the bottom and 2,300 at the top. So free tech is up here, because free tech is free to fly away. So I need to find my percent hydrolyzed reduced, I need to find my percent free tech, and then I can use both of those to find my radiochemical purity. So I'm going to do hydrolyzed reduced first. My hydrolyzed reduced is at the bottom, so whatever I want to find a percentage of, that's what goes in the numerator. 1,000 divided by the total, that's where most mistakes are made. 1,000 plus 21,300, times that by 100. We've got 1,000 divided by 1,000 plus 21,300 times 100. We've got 4.5%. Now my free tech, same thing. My free tech counts are 2,300 over the total 2,300 plus 42,500 times 100. 2,300 divided by 2,300 plus 42,500 times 100 equals 5.1%. So I've got my hydrolyzed reduced, I have my free tech. Going back to the problem, it says, what is your radiochemical purity? Those are impurities. So I have to take 100 minus 4.5 minus 5.1. My answer is 90.4% purity. All right, we're going to keep on going because we still have 24 minutes. Keep the energy up. Our well counter, has an efficiency of 88%. We have to convert CPMs to DPMs. CPM divided by efficiency equals DPM. So if my wipe is 200 and my background is 22, 200 minus 22 divided by 0.88. Now if I accidentally multiply, I know it's going to be wrong because my DPMs are always going to be higher than my CPMs because we have to correct it for its inefficiency. 200 minus 22 divided by 0.88. My counts are 202 DPM. Same thing, white 450, background 11, divided by 0.88. 450 minus 11, divided by 0.88, 499 DPM. All right, we're going to skip that. Instrumentation. So we still have instrumentation and what else do we have? Radiation safety. Okay, instrumentation, percent error. Percent error, we do this with our dose calibrator quality control. Percent error is going to be expected minus actual divided by expected. Expected is what you calculate. Actual is what you actually get. What is the percent error if the expected reading is 4.8, actual reading is 4.6? I'm going to take my 4.8 expected minus my 4.6 actual divided by my 4.8. And times that by 100. 4.8 minus 4.6 divided by 4.8 times 100. And I get 4% error. Less than 10%, you pass. Let's do another one. You're doing a constancy test. The actual reading is 66.4 microcuries. You think you expected it, you calculated it to be 68.4. So I have to take my expected, 68.4, minus my actual, 66.4, divided by my expected of 68.4, times it by 100. And I get 3%. By the way, this is an absolute value. So if in your numerator your expected is less than your actual and you end up with a negative number, absolute value means disregard that and make it positive. It'll always be positive. All right, correction factor. We do this when our linearity or our geometry fails, when it's over 10%. So it's over 10%. Here's our question. Technologist is performing a geometry test and gets the following results. Expected was 22.4, actual is 19.1. First thing I'm going to do is make sure that I have to calculate a correction factor. I only have to do that if it's over 10%. So I'm going to do my percent error first. I'm going to take my expected 22.4 minus my actual 19.1 divided by my expected of 22.4 times it by 100. My percent error is 14.7%. Yep, hit a correction factor. So correction factor is expected over actual. And if you forget, just remember you're always going to say expected first. So percent error equals expected minus actual divided by expected. So expected always comes first. Expected over actual. So my expected reading is 22.4. My actual reading is 19.1. We're not turning this into a percent. This is a factor. What do we do with factors? We multiply. Anytime you see the word factor, that means multiply. Just like anytime you see the word cathode, that means electron. 22.4 divided by 19.1, my correction factor is 1.17. That means every time I use that 10 ml syringe in my dose calibrator, I have to multiply it by 1.17. All right, another one. A technologist is using a dose calibrator that requires a correction factor of 1.17, and the dose reads 12.5, so what's the true reading? Correction factor, I multiply. 12.5 millicuries times 1.17. My true reading is 14.6 millicuries. All right, energy resolution. Energy resolution. We need this when we set our window. The more narrow our peak is, counts, the better the energy resolution. If we collect the same amount of counts and give awful energy resolution, it's gonna look like this. Look how low my counts are. So we're gonna evaluate how wide or narrow that peak is. And we're gonna do that with the full width half max. So here's the maximum, here's the half maximum. I'm gonna take the width at half its maximum and see how wide that is. So in my problem, what is the energy resolution? Technetium, the full width half max is 17. 17, I have to divide that by my energy. Energy of technetium is 140. Times that by 100, gives me a 12% energy resolution. Let's do it again, this time for cesium. What is the energy resolution of a counting system for cesium-137? The full width half max is 85. So I'll take my 85 divided by 662, which is the energy of cesium-137, times that by 100, it gives me 13%. So fun fact, cesium-137 does not actually have an energy of 662 keV. Cesium-137 is a beta negative emitter. It decays to barium-137M, which is metastable, which decays to barium-137 with a 662 keV gamma ray. So nobody knows that except for the 11 of you and me. Because we're nerdy enough to be here on a Wednesday night to do this. So we might as well know. But seriously, it doesn't. And, you know, it bothers me that everybody thinks that. All right, sensitivity. When you think sensitivity, think, what is the count rate per the amount of activity I'm giving? So it could be counts per minute or counts per second in the numerator, and it could be millicuries, microcuries, becquerels, kilobecquerels, any unit of activity in the denominator. So this particular problem, I have 110 microcuries, and I put it on the gamma camera, and it's giving me a count rate of 512,635 with a background of 956. So count rate is in the numerator. I'm going to take my 512,635, subtract my background of 956, and then I'm going to divide that. Those are my CPMs. I'm going to divide that by my activity of 110 microcuries. My unit is CPM per microcurie. So you plug that in your calculator. And you're going to get 4,652 CPM per microcurie. All right, one more. You have 145 microcurie source. It gives you a count rate of 48,635. Background is 479. Count rate, 48,635 minus my background of 479. That's my CPM. Divided by my activity, 145 microcuries. My unit is CPM per microcuries. And I plug that in my calculator, gives me 332. That's my sensitivity. All right, matrix and pixels. How do you figure out how many pixels in your matrix? You just multiply them. 64 by 64 matrix, 64 times 64 is 4,096. 128 by 128 matrix, I've got 16,384 pixels. 256 by 256, I've got 65,536 pixels. Now, how do I figure out pixel size? All you have to do is think about what it's asking you. It's saying, how many millimeters are your pixels? So my field of view is 380 millimeters, and my matrix is 128 by 128. I don't multiply that though, because it's 128 going this way and 128 going this way. So I just divide by 128. Gives me 3 millimeters per pixel. That's the size of my pixels. If I change my matrix to 64 by 64, again, 380 millimeters over 64 pixels. When I change my matrix size so I have fewer pixels, it makes my pixels bigger. So now I have 6 millimeters per pixel. Now what happens when I put on a zoom? When you put on a zoom before acquiring, that means you want more resolution. The way to increase resolution is to make your pixels smaller. So So when you put on a zoom, you're making your pixels smaller. So we're gonna do the same thing, 380 millimeters divided by 64 pixels gives me 6 millimeters per pixel. When I put on that zoom though, I'm gonna divide it by 2, making my pixels smaller, 3 millimeters per pixel. All right, expect acquisition time. I think that's the last one in this section. Then we have to do time, distance, and shielding. Expect acquisition time. You're performing an MPI with a dual-headed camera. You're going to get 64 images, 10 seconds per stop. How long is your acquisition? All right, I have a conversion here. 10 seconds equals 1 stop, okay? Which is great, but I don't know how many stops I have. And it's asking how many seconds. So I need to first figure out, well, how many stops do I have so I can use this conversion? But I know I'm getting 64 images, and it's a dual-headed camera. So every time my camera stops, I get 2 images. So 64 divided by 2 equals 32 stops. Now I can use my conversion. I have 32 stops. Stop goes on the bottom, seconds on the top. 10 seconds per stop, stop cancels. I end up with 320 seconds. If I wanted to, I could convert it to minutes. It'd be 5.3 minutes. All right, let's do another one. You want to obtain 3 million counts in your spec study. Your count rate is 200,000 counts per minute. You have a single head camera, and you plan to do 64 stops. How long is your acquisition, and how many seconds per stop? All right. So I'm looking at this problem and I am completely overwhelmed. But I remember Sybil telling me, find your conversion. So I'm looking, I'm like, where is my conversion? 200,000 counts equals 1 minute. I have a conversion. 200,000 counts equals 1 minute. Now, what do I have in here that I can use my conversion? I have 3 million counts. And I know that one of the questions is, how long is my acquisition? So if I start with that 3 million counts, I can use this conversion of 200,000 counts in 1 minute. Counts cancel. 3 million divided by 200,000. That gives me 15 minutes. My acquisition is 15 minutes long. Okay, I've done the first part. Now what do I need? Now I need to know how many seconds per stop. How many seconds per stop? Well, I know how many stops, it tells me. Okay? So I know I have 64 stops. But I don't know how many seconds I have because I'm in minutes. But I know I can convert my minutes to seconds. 60 seconds, 1 minute. I have 900 seconds. I throw my 900 seconds in here. 900 seconds for 64 stops. Each stop is 14 seconds per stop. Now, if you get this question on your NMTCB exam, you already passed. You just like hang it up because that's a hard problem. But you guys got it. All right, we're going to end with radiation safety, time, distance, and shielding. Time problems, conversion problems. I always tell my students on the very first day of nuclear medicine school, because they're all afraid of math, I'm like, math, 70% of math in nuclear medicine is conversions. And if you think about everything we did today, 70% of what we did was conversions. Maybe 20% is equations, and then 10% is decay. And if you got your shortcuts down, you're golden. All right, so these are conversions. You're holding a syringe of technetium in your hand, putting off 3,258 MR per hour. What is your total exposure after 30 seconds? Find your conversion. 3,258 MR equals 1 hour. Have to start with 30 seconds. Need to get to hours. Seconds on the bottom, minutes on the top. 60 seconds is 1 minute. Seconds cancel. I'm at minutes, I need to get to hours. Minutes on top, I need to put it on the bottom. Hours on top. 60 minutes, 1 hour, minutes cancel. Now I'm at my conversion. I'm going to put my hour on the bottom, MR on the top. Let's go to my conversion. 3,258 MR in 1 hour. 30 times 3,258 divided by 60 divided by 60. In the interest of time, I'm going to give you the answer is 27 MR. You're scanning a bone scan patient, receiving 0.05 MR per hour. How much do you receive after 30 minutes? Find your conversion. 0.05 MR equals 1 hour. We're going to start with 30 minutes. I have to get to hours first. Minutes on the bottom, hours on the top. 60 minutes, 1 hour. Now I can put my conversion in. 0.05 MR, 1 hour. Hour canceled. Answer 0.025 MR. All right, one more in time, then we're moving to distance. We're going to ask it a different way. Your therapy patient is putting out 20 MR per hour at 2 feet. How long can you stand at this distance? So even though I'm given distance, doesn't mean I have to do distance, because it's telling me I'm not changing my distance. So that's irrelevant information. 20 MR per hour, how long can you stand there before you get 5 MR? Conversion, 20 MR equals 1 hour. Now I start with 5 MR, I'm at MR, I'm at my conversion, but now MR goes on the bottom, hour on the top. 20 goes down here, MR cancels, I'm at 0.25 hours. Distance. ID squared equals ID squared. Don't make it any more difficult than it needs to be. ID squared equals ID squared. There's 4 variables, you get 3. You just have to find the 4th one. If your technologist is exposed to 3 MR per hour at 3 feet, what's going to be the exposure rate at 4 feet? So my 3 MR per hour goes with my 3 feet, and I have to square it. Always square the distance. We're trying to find the new exposure at 4 feet. Divide both sides by 4 feet squared. My new exposure is 1.7 MR per hour. Okay. If you're working next to hot lab, you're 8 inches away, and it's 2 MR per hour. How far away should you sit so you're getting background, 0.02? Now I'm going to find my distance. So 2 MR per hour times 8 squared equals 0.02 times d squared. Divide both sides by 0.02. Have 6,400 equals d squared. Take the square root of both sides. D equals 80 inches. Now, if we put time and distance together, we have to do distance first, because time is a conversion problem, and you can't do time until you have your conversion. So, we are working next to a radioactive source. It's putting off 40 MR per hour at 1 foot. How much exposure do you receive if you stand 3 feet away and you stand there for 90 minutes? When you do your distance, just ignore the time. We can always go back and do that. So 40 times 1 squared equals new exposure rate, 3 squared. Divide both sides by 3 squared. New exposure rate is 4.4 MR per hour, which is my conversion. Now I'm there for 90 minutes. I have to get from minutes to hours. 60 minutes is 1 hour. I'm at hours. I can put in my conversion. Hours cancel. My answer is 6.6 MR. All right, last section is shielding. We are on the home stretch. Half value layers, same thing as half-life, except it's the thickness of the shielding to stop half. If you have a syringe that's producing 20 MR per hour, what will be the exposure if you add 3 half-value layers? All you have to do is take your 20 MR per hour, divided by 2, that's 1 half-value layer, divided by 2, that's 2 half-value layers, divided by 2, that's 3 half-value layers. That's the same as 20 divided by 2, 3 half-value layers to the third. Comes out the same, 2.5. All right, we're going to set this up like the decay equation now, because it's the same equation. I sub T is the activity after you put shielding on, just like A sub T is the activity after decay has occurred. I sub O is the intensity without the shield, just like A sub O is the activity before decay occurred. So I sub O is always going to be the higher one. So the half-value layer of I-131 is 0.2. Your half-value layers will be given to you. You do not need to know half-value layers, but you do need to know half-lives. You have a source that has an exposure rate of 125 MR per hour, you're gonna put a 1.3 millimeter shield on it. So I'm looking for I sub T. I sub T equals 125, my exposure rate. E to the negative 0.693 divided by the half value layer, which is given, 0.2, times it by the thickness of this fringe, 1.3. I sub T, when you plug that in your calculator, is 1.4. All right, let's do a little bit of a shortcut here. Tax source is putting out 2,364 MR per hour. You're gonna add 0.9 millimeters of shielding, and each half value layer is 0.3. So when I see that, I'm thinking, I think I'm adding 3 half value layers. How did I figure that out? One half value layer is 0.3, the second one is 0.3, the third one is 0.3, all those together equal 0.9, and that's what I'm adding. So if you take your total thickness divided by your half value layer, that gives you the number of half value layers. I'm adding 3 half value layers. So I can take 2,364 divided by 2 3 times, or divided by 2 to the third. That's the exact same thing. And when I do that, it's 296. I could have done it the exact same way. I sub T equals 2,364. E to the negative 0.693 divided by half value layer 0.3 times 0.9, and you're going to get 296. It's the exact same thing. All right, last one. The half value layer for tech is 0.3, source is 365, you add 1.4 shielding. To find the number of half value layers, I take 1.4 divided 0.3, I'm adding 4.67 half value layers. All I have to do is take 365 divided by 2 to the 4.67. My answer comes out to be 14.3. Of course, I could have done I sub T equals 365 e to the negative 0.693 divided by 0.3 times 1.4. I'm going to get the same answer, 14.3. And now, to really blow your mind, this is the same equation as the decay equation. Do you know how many half-lives have elapsed? You can do this as well, which is, freaks me out. All right, thank you guys for attending. I'll stick around for the next minute or so to answer questions. Other than that, I hope to see you at a